Hello, I'm Chetoui, a PhD candidate in the School of Engineering at Brown University. Today I'll be presenting about the alternating blind identification of power sources for mobile SoCs. The outline is as follows. We're gonna start with an introduction, then I'm gonna introduce the problem formulation. Afterwards, I will walk you through the related work. Then I will introduce the alternating blind identification of power sources. Then we're gonna discuss the results and the summary.
For faster systems on chip has accelerated scaling trends. So as technology scales down, the power density considerably increases, raising critical power and thermal challenges. As you can see on figure 1, showing the power density versus the scaling trends, basically it shows on the x-axis the technology node being used, and on the y-axis is showing the power density, that is the watts dissipated per millimeter square. And as you can see, as technology scales down, the core power density exponentially increases. Additionally, the increased processing capability of mobile devices has enabled new applications that require intensive computation. And actually, this is even more challenging for mobile devices due to their form factor, the multiple sources of thermal emergencies, but also their limited cooling capabilities. Um, so, as a result, all of this is leading to a considerable power density increase, raising critical power and thermal challenges. Actually, elevated power dissipation and chip temperature levels, they trigger performance throttling mechanisms, um, making such temperature levels a major performance bottleneck. As a result, the ability to measure power consumption at different hardware units is essential for the operation and improvement of mobile SoCs. However, due to the complexity of adding current sensors, mobile SoCs they usually lack the ability to sense the power at the hardware unit level. However, they are usually enabled with embedded thermal sensors to measure the temperature at the hardware unit level. So there is usually at least one thermal sensor per hardware unit. For instance, in figure 2, I'm showing an ARM big little architecture of a CPU. As you can see, the CPU is composed of 4 little cores, 3 big cores, and 1 boost core, which is shown in red. So usually in a cluster of 8 cores, you would at most find 1 to 2 current sensors that could be used to measure the power. However, you could find up to 14 thermal sensors for the whole CPU. In order to understand the problem formulation, we need to understand the physical relationship between power and temperature of a chip, which is actually governed by the heat diffusion equation shown on the top right side. So the heat diffusion equation is a function of many variables, including the density and specific heat of the material, as well as the thermal conductivity of the chip in a specific location. So if we perform a spatial and temporal discretization, we're gonna get the state space model or simplified version of the heat diffusion equation, which is shown in the red rectangle. So basically, it expresses the temperature at time k in function of the temperature in time k minus 1 and the power in time k. And the two important matrices in here, modeling matrices, are the A and B matrices. So the A matrix is actually the thermal conductance matrix, which represents the natural response of the system in the absence of power. The B matrix, on the other hand, represents the forced response matrix, which is composed of both thermal capacitance and thermal conductance. On the other hand, so the TKs and the PKs are vectors that denote the temperature and power of the SoC hardware units at time k. So basically, the problem in here is that the A and B matrices are unknown because they are design specific, and the PK vector, which represents the power values for each one of the hardware units, is also unknown because of the inexistence of current sensors as explained earlier.
There are three different approaches to identify the state space model matrices. Um, so there is the design-based approach, and it's based on pre-silicon data and requires access to the design proprietary information such as its layout and gate level netlist, its materials, and heatsink configuration. So the problem with this approach is that it's design specific since it requires access to such data. And as well, it's prone to errors related to variability in the semiconductor manufacturing process. The runtime based approach actually considers the processor as a gray box, and it tries to identify the state space models based on physical measurements. So the issue with this technique is that it makes the assumption that sensors like fine grained sensors are available to measure the power. The other approach is the blind identification approach, which makes no assumption about the availability of modeling matrices and the fine-grained power sensors. So this approach basically relies only on the total power and the fine-grained thermal sensors to estimate both the modeling matrices and the power sources. The alternating BPI consists of an offline learning step and a runtime estimation step. During the offline learning, we try to estimate the A and B matrices that constitute our state space model. So as shown in this equation, we try to estimate A and B such that Tk equals A times Tk minus 1 plus B times Pk. And then after estimating the A and B matrices during the runtime estimation, we use the per unit thermal measurements from the different cores or the different sources of power and the total power consumption to estimate the per unit power consumption. So as shown in this figure, on the left side, the inputs of the alternating BPI would be the total power measurements or the total power consumption of the different units, and the per sensor temperature measurements for each one of the cores, and then it outputs the power per core for each one of the temperature measurements that we have given as input. Start by estimating the A matrix, which represents the natural response matrix. So basically, the A matrix describes the behavior of our circuit in the absence of any power source. So basically, we estimated by using a transient temperature traces that basically describe the cooling process. So as you can see in the figure, for instance, in here, on the y-axis, we have the average SoC temperature. And then the different colors, they correspond just to different experiments. So basically, to estimate the A matrix, we need to collect similar temperature traces where we could see the cooling process of our different hardware units. Because the cooling process actually kind of like has information about the conductance of our circuit, and the conductance of our circuit, it's what represents actually the A matrix. So we achieve this by stressing the cores with the workload, and then by forcing basically the different cores afterwards to an idle state where Pk, the power consumption, is equal to 0, we get the following version of the state space model. Afterwards, mathematically, this is identified by using a least square minimization, where we try to minimize Tk minus A Tk minus 1 under the constraint that the A matrix is positive. To estimate the B matrix, we start by making initial guess about its value, then we could improve it later in step 3, 4, and 5. To make an initial guess about the B matrix, we use the steady state case where the temperature in time k is equal to the temperature in time k minus 1, which gives us equation number 3 from our state space model, which could be further simplified to equation number 5, where the steady state temperature is equal to the R matrix times the power in the steady state case. One of the characteristics of the R matrix, which represents the thermal transfer matrix, is that it's a symmetric matrix with maximum values in the diagonal. So using these characteristics of the R matrix, we could come up with the initial guess about the B matrix shown in the second step. To make a better estimate of the B matrix by alternating between two different steps, the P step and the B step. In the P step, we try to estimate Pk, which represents the power consumption per SoC unit at time k. So given a guess of the B matrix, we try to solve the quadratic programming problem shown in line 4 of algorithm 1. So basically we try to minimize this equation given by or derived from the state space model, where we try to minimize b times bk minus tk minus a times tk minus 1, such that the total power consumption of the different units at time k is equal to the total power given as input in time k. Uh, and then basically the other constraint is that all the pk values should be positive because power should be positive. The number of unknowns in here, since we are trying to find the power, is equal to the number of power sources times the number of time samples. Then in the next step, we try to estimate, or in the B step, we try to estimate the B matrix given the pk from line 4. So we solve this basically using the least square minimization shown in line 5, where basically given pk and given the A matrix that we estimated earlier, we try to minimize this least square problem in here, where we have bpk minus tk minus A times tk minus 1. So the number of unknowns in here are different and the constraints as well are different. In here, the number of unknowns are much less than in step 4 because we are trying to estimate the B matrix whose dimensions are equal to the number of samples square. And then basically the idea is to keep alternating between these two steps because we are trying basically to estimate the power and the B matrix at the same time. And the assumption in here is that the more accurate we estimate the power, the more accurate we could estimate the B matrix, and the more accurate we could estimate the B matrix, the more accurate we could estimate as well the power. And that's why we keep alternating between these two steps. Finally, in the runtime estimation, the A and B matrices are fixed. And basically, we use the estimates of the A and B matrices as well as the total power and the temperature per hardware unit to solve the quadratic programming of the P step that we just explained. And this will result in the power per unit for each one of the time samples. And test the accuracy of the alternating BPI, we use Hotspot, which is a thermal simulator. As you can see in figure 3, we are showing the verification and testing flow of the alternating BPI. So basically Hotspot, the thermal simulator, takes as input the layout of the circuit that we are trying to use, as well as an input data which consists of the per unit power consumption. And then Hotspot actually gives as output the per unit temperature of the different units, which is given as input to the alternating BPI along with the total power consumption of the different units. And then the output of the alternating BPI is actually the estimated per unit power, which is the pk vector that we already discussed. And then the estimated per unit power of the alternating BPI is compared to the per unit power that we have given as input to the Hotspot simulator to try to compute the accuracy of the proposed technique. In order to estimate the accuracy of the proposed technique, we use 3 different benchmarks: a 2x2 mesh composed of 4 homogeneous units, a 3x3 mesh composed of 9 homogeneous units, and a big little plus GPU architecture, which is a heterogeneous system composed of 6 units. And we compare our technique against BPI and BPI SS from the literature. Table 1 actually shows the power estimation error, which is supposed to be more difficult as the number of units increase. For instance, you could see that the estimation error for BPI increased from 4.4 to 9.9 when increasing the number of units, which is also the case for BPI SS, whose estimation increased from 4.4 to 6.5. On the other hand, the alternating BPI was able not only to achieve a better accuracy, but also to maintain the same accuracy of 2.4%. On the other hand, Also the estimation is supposed to be more difficult when moving to a heterogeneous system. For instance, you could see that the estimation error increased to 11% for BPI and to 8.8% for BPI SS, while the alternating BPI was able to get the estimation error as low as 1.9%. As a result, not only the alternating BPI is able to get a better accuracy in estimating the power consumption of different units, but also it's able to maintain the same accuracy level even when we increase the number of units or when we use heterogeneous systems. In this figure, we compare the accuracy of BPI SS against alternating BPI in predicting the power per cluster for the heterogeneous system, the big little GPU, which has 6 clusters basically. So the actual power values are given in blue, the BPI SS estimations are given in green, and the alternating BPI is given in red. And as shown in the figure, you could see that the estimation accuracy of the alternating BPI is substantially better than the BPI SS, and it's equivalently accurate for the different clusters. To validate our results further, we use a commercial mobile SoC. The setup shown in figure 5 is used, where we use the 865 hardware development kit and the Monsoon power monitor to measure the total power consumption of the board. Next shows the alternating BPI estimated power per SoC unit of the Snapdragon 865. The first two subfigures show the data used as input to the alternating BPI, which is composed of the temperature per cluster and the total power consumption. And as shown on the third subfigure, the alternating BPI was able to retrieve or identify the power consumption per cluster. And given the characteristics of each one of these blocks, we were able to validate these results. So for instance, looking at the last two pulses in here, the power consumption, even though the temperature of the little cluster shown in black was substantially or relatively high, its power consumption was estimated to be much lower than the power consumption of the performance cores shown in green and in blue. Using the same development board, we were able to conduct a power characterization of different mobile apps as shown on both figure 7 and 8, where in figure 7 we show the estimated power consumption per SoC unit for the different mobile apps, and in figure 8 we show the percentage power consumption per SoC unit. And there are a lot of insights. So for instance, in here, we were able to conclude that the CPU really remains the main source of power consumption, with power consumption representing around 60% to 70% of the total power. Secondly, the little cluster actually plays a major role in saving power, with a power consumption up to 5x less than the power consumption of the big and the boost cores. As well as the fact that the CPU frequency boost actually has a very low power efficacy. So actually the 20% boost of the big four actually could lead to up to 2x power consumption as compared to the regular big cores. And then finally, the augmented reality apps actually have a really high CPU power consumption with a much lower GPU power consumption as expected. Finally, to summarize, in this work, we proposed a technique for blind identification of power sources that only relies on the temperature values and the total power consumption to estimate at the fine-grained level the power consumption of the hardware units. The proposed approach decreases the estimation error to 1.9% as compared to 11.2% for BPI. The accuracy of the proposed work was verified using simulation and validated using experimental data on a commercial development board. The new approach was used to characterize the per-unit power profile of several benchmarking apps on commercial SoCs, including CPU, GPU, artificial intelligence, virtual reality, and augmented reality apps.